Hello, I'm Mary Ito, and welcome to the CRAM podcast. CRAM is an acronym for Communicating Research and More, which is what we try to do on this podcast. A lot of exciting research and groundbreaking ideas never reach the public, but they have the potential to change the way we think and act. Well, it is the stuff of imagination and of possibility. And every area of endeavor, whether it's the sciences, the arts, or the humanities, have all been inspired and informed by it. I'm talking about space, the universe, the mysterious beyond. It involves the biggest of the big, that would be infinity, and the smallest of the small, as in neutrino. And there's no one more passionate about the exploration of space than Sarah Gallagher. Sarah is an astrophysicist. She's a professor of physics and astronomy with Western University, and she's also a science advisor to the Canadian Space Agency. And she joins us to explain and to have us imagine some of the great mysteries of the universe. Hello, Sarah.
Hello, Mary. Thanks for having me.
Oh, I am thrilled to have you on. Do you know, I was thinking about it and I thought, gee, I wish I had met you at a cocktail party, because I would love to know what people's reaction is when they find out what you do.
It's really funny, actually. It depends if I tell them if I'm an astrophysicist or an astronomer.
Oh.
So if you tell someone they're an astronomer, it's a choice. For example, remember when we used to go on planes and talk to people who were sitting in the chair next to us?
Yeah.
So if you tell someone you're an astronomer, it's a commitment. You're saying, I am willing to talk to you for the next, however amount of time, because it's usually not a short conversation. But if you say astrophysicist, it's kind of hit or miss, because that can be something that can be a little intimidating, I think.
Oh, and is it because people don't really know what that is?
I think that's probably true. It just sounds hard. Whereas astronomy, people love space. They love the stars, and they've seen those beautiful images from the Hubble Space Telescope. So I think it just feels much more accessible, even though I would use both of those words to describe what I do.
Well, people do love space, because when I was doing the version of this podcast as an actual festival that people came to and we were sharing research, we had a couple of space topics and they were booked right away. It was standing room only. Just people love learning about the universe. And, I am curious about it as well, but I'm also curious about the way an astrophysicist's mind works, like the way your mind works. How did you get interested in space in the first place?
So I think I also just had that intriguing, that set of questions where you just try to wonder, what's going on? What does it mean? And it seems weird. And for me, it wasn't something I was particularly excited about or particularly engaged with until I got to university. And I studied physics because I really like the structure of physics and the way that you can use it to explain how things work. It's very logical, which I really liked as a student. And I took an astronomy course just for fun because it sounded cool. And then what I loved about it was that, and this was quite a while ago, but at that time, and it's still the case, when you study astronomy, you're just confronted immediately with the boundaries of knowledge. It's so obvious that we don't know so much about the universe, which makes it really exciting. As a student, you don't think, oh, they'll have figured everything out by the time I get to do some of it. That's just not even a question, because there's still just, we don't know what the mass of 75% of the universe is. It's kind of a big deal, right? And people have been trying really, really, really hard to find it, and they haven't been able to. So there are just these big questions, and they're in your face. And even before you study it at a very high level, it's really clear that we just have big questions and we don't know a lot about the universe. So for me as a student, that's just very, very exciting.
And, do those big questions, do you think they require a big imagination?
Oh, that's such a good question. So one thing that I think surprises a lot of people is that I consider creativity to be one of the characteristics of a scientist that is really, really important. I think often people think creativity is limited to the arts, but it's really necessary in a scientist as well. And so I think it does require a big imagination. And one of the things that I love about studying astronomy is that you can't do it in the lab. So most of it, there's certain parts of it you can, but lots of it you just can't do it in the lab, right? We don't have black holes in the lab, so
Right.
we don't have billion-degree plasmas. There's just these extreme environments, and if you want to study them, if you want to understand how matter operates in those weird regimes, then you have to leave the Earth. And if you can't leave the Earth physically, I mean, you leave it with your telescopes. You peer out into the universe in order to study those areas. So that's one thing that I think is that I really love about it is just, and the scale of everything. The universe is huge. I mean, our solar system is huge, right, compared to our the bounds of our normal life. But the universe is enormous.
Exactly. Well, this is it. So, I mean, this is all to me about getting into your mind as well. I wish I could be right in your mind to see how it works, because in the introduction, I talked about space being, infinity, right? The biggest of the big, infinity.
It's actually not infinite. Just
Oh, it's not infinite.
No.
Oh,
the universe is not infinite. It's really, really big, but it's not infinite.
When was this? When did this happen? I thought it was infinite.
Well,
did I learn the wrong thing?
It's it's enormous and it's huge, absolutely, compared to everything that we think about. But
right.
But the universe has an age, and so it's not infinite because we look out in the universe, we look back in time, and there's a point at which we can't look any farther. And it's not because our telescopes aren't good enough. It's because that's it. That's the boundary of what we're able to see. So it's really large, but it's not infinite.
So wait a second, then, if that's the boundary, what comes after the boundary?
I don't know. So it's unknowable in a fundamental way, where in the same way that we can't know what happens when something falls into a black hole.
So wait a second.
We can't know.
All right. So just because it's not infinite, though, does that mean it's finite?
Yes.
So, okay. All right.
Yes. It has a boundary. So, and the boundary, in some sense, you can think of it as being the age of the universe. So we can look back to the Big Bang, but then we can't look past that.
Wow, that's a biggie that I just got corrected on. I like that.
Mm-hmm.
So the thing is, it's so big. Like if you were to say to me, Mary, imagine 100 things in your head, right? I could probably do that. And if you said, well, imagine now 1 million. I'm not sure I could imagine 1 million things in my head. Do you know what I mean?
Yep.
And then you say, imagine the universe. There's no way. Like I can't even. So I just think about your mind and then how you're able to encompass and imagine all these things about the universe, like black holes even. How do you do it? How do you get your head around all that?
Yeah. So I think that you have different frameworks for measuring things. So, and it depends actually on the kind of science you do, the kind of astronomy you do. So if I'm somebody who studies stars, I have our sun. And our sun is, it's sort of a medium-sized star. It's, halfway through its lifespan. It's 8 light minutes away from the Earth. The nearest stars are a couple light years away. So those are sort of manageable scales, even though if we talk about the sun in terms of how many kilograms it is, that number is huge.
Mm-hmm.
But if I think, okay, the sun is what I'm starting with, that's my basis for comparison, then I can envision the next star and other solar systems and planets in our solar system. And similarly with I'm an extragalactic astronomer. That means I study things outside of our galaxy. So I start with our galaxy. And our galaxy is about 100,000 light years across. And we're about 2/3 of the way out in the disk of it. You can think of it as being shaped kind of like a fried egg. And we're in the white. We're like sort of 2/3 of the way out in the white of the fried egg. And so I have that as my model. And then I say, okay, the next nearest galaxy that's kind of like ours is the Andromeda Galaxy. And I know how far away that is. And so we have these, I think, standard measures, and then ladders that allow us to sort of build our way out. Because it's absolutely true. When we think of the size of the universe, I don't have a picture in my head of a volume. I mean, it's always relational, I think, to things that are easier to grapple with.
It almost makes me wonder too, when you're thinking of things on such a grand scale and like light years away, when it comes to things on this earth, does it seem really, really small? You know, like I've got to travel 100 kilometers. Nothing. That's nothing
nothing.
today.
Yes. It's true. So there's ways in which the earth seems really, really tiny and other ways in which it seems really, really special. So I think one of the ways in which I think about it is that the earth as a terrestrial planet with liquid water around a medium-sized star that has an amazing atmosphere that's able to sustain life. I mean, that is so special. And so in that sense, it's amazing and incredible. And even though it's relatively small compared to the size of the galaxy, the size of the universe, it's such a special place. And we also really care about most of the information we get about the universe is from light. And so in order to interpret that light, you have to study individual atoms. And, oxygen in space and oxygen on the earth, it's the same oxygen. So there's ways in which you connect what you see in space to what's on the earth because it's the same physics and it's the same stuff.
Mm-hmm. If you were to look back over, I don't know, let's just say half a century, what would you say has been the most important discovery in space or the most important discoveries in space in the last half century?
Wow. That's a tough question. Those are fighting words. So whatever I say, somebody's going to get upset. So the biggest, in the past 50 years, I think, so one of the most incredible discoveries was what's called the cosmic microwave background radiation. So that basically is, if we look everywhere, what we do is we see this glow, and it's the glow from the early universe. The glow from when we had this really hot, thick soup, which was the entire universe was this hot, thick soup, plasma, like what we have in the inside of the sun. And it expanded and it cooled. And at some point it became transparent. And then the light could travel through the entire universe. And that was detected in the 50s. And it was an amazing discovery because that's part of what told us that the universe started with a big bang and that it's finite, it's not infinite, and that it has changed over time. So I think that was probably one of the most fundamental discoveries just about the nature of the universe that we live in. I also, of course, was very excited when, I would mark black holes as well.
I was thinking you might say that. Yeah. When was it when they were actually proven?
Well, it depends who you ask. So it's there were lots of different sort of pathways to finding black holes. One of the definitive ones that I think many people would agree with, and it was the subject of a bet with Stephen Hawking and Kip Thorne, who are two well-known theoretical physicists, was the discovery of what's called an X-ray binary. So what that is that's a small compact object, which could be a black hole, and there's a star that's orbiting around it. And the star basically has the outer layers of it get pulled by the black hole in the center, and then they swirl around, and it glows off, and it glows, and it at 1,000,000 degrees hot gives off lots and lots of X-rays. And so there was one of those X-ray binaries, and because it had that star moving around it, you can measure the mass of the thing it's moving around, even though you can't see it. And so at that point, the fact that the mass of that in that X-ray binary of the black hole could be measured, and you couldn't see anything, and it had a certain value. That was the first, I would say, the first example of a measurement of a black hole that everyone was like, yeah, that's a black hole.
See, this is what I find so incredible, that you can prove something like that indirectly, right?
Mm-hmm.
It's not that you could see it. It's because of the circumstances around it that you could measure the black hole. I find that so mind-boggling. Tell us about black holes and what we know about them.
So it's so interesting. I want to say we know a lot and we know almost nothing. So because both things are sort of true. And I think actually to your point about trying to figure things out indirectly, that's like the story of astronomy, because all we can do in most cases, is look at the light. So we look at the light and we try to figure out what it means. And what we really want to know is, what's its mass? How big is it? What is it made out of? What is its structure? But all we get is the light. So to some extent, it's like it's like CSI, right? So you walk into the room and you say, all right, what happened here? I'm trying to, reconstruct the series of events. That's like the story of astronomy. So that's, we're used to it. That's kind of what we do. But in terms of what we know about black holes, it's we can't see black holes directly because the definition of a black hole is that it's so compact and massive that not even light can escape. But it's still there and it still impacts the environment around it. So what we actually usually see is the influence of the black hole on the matter around it. So you could have a star that's orbiting a black hole and you may see nothing there, but you just see the star's got a wobble. And so there's a black hole there. And then also what you can see, and what I study big black holes in the centers of galaxies. Those are called quasars. And those big black holes, when they're growing, they have this disk of gas and dust that's basically swirling around. And it's losing energy, and eventually it will fall into the black hole. But before it does that, it gives off a huge amount of light. And so these objects are super bright. We can see them really billions of light years away because they're really, really bright. So we know that these black holes live in the centers of distant galaxies. Every massive galaxy, as far as we can tell, has a big black hole. Our Milky Way has a big black hole in the center. And they grew by basically gas and dust and stars and things like that swirls in and falls into the black hole. And that seems to be something that is just a thing that happens to every galaxy that goes through this phase where it's growing a black hole and it shines and it's super bright and then it gets quiet. And that seems to happen all over the place.
And now, when something goes into the black hole, does it cause the black hole to get bigger? Does it expand?
So yes, but in a sort of indirect way. So it gets more massive. And so when you say, how big is a black hole? That sounds like a simple question, but it's a little complicated because it kind of depends what you mean. So, but we often define the size of a black hole by what's called the event horizon. And that's the surface around the black hole where the speed of light is the escape speed. So that means past that event horizon, light cannot escape. And so to some extent, once something passes that event horizon, we don't know what happens. So It makes the black hole get more massive. And then also the size of that event horizon depends on the mass of the black hole. So a more massive black hole has an event horizon that's bigger, but it's sort of the size it's really the mass that's driving the size. So yes, it gets bigger, it gets more massive, and it also gets a bit bigger.
And is its behavior consistent through time or not?
There's different things that can happen. So there's something that's called the no-hair theorem, which is, we've got all sorts of crazy names for things in astronomy. What it means is that they say black holes have no hair. And
I didn't know they did have it. Yeah, I didn't even think there was that really? Analogy there.
But it refers to the fact that they're actually quite simple. So if I want to describe a black hole, all I need is 3 numbers. So I need to know how massive is it. I need to know if it's spinning, and I also need to know if it has a charge. And in general, black holes in the universe, even if they had a little bit of a charge, if they had a negative charge, then it would attract positive charges, and so it would so basically they're all 0. So it's sort of 2 numbers then. It's the mass and the spin. And so black holes can change over time. They can become more massive. And they can also, their spin can change. And the way the spin changes is that if you have a black hole and it's not spinning, and you send something into the black hole that's rotating around, then it can spin up the black hole as that material falls into it. So those are ways in which it can change over time.
Oh, so have they existed as long as we know, since the beginning, or?
Well, maybe. So,
Oh.
so it could be the case. So this is one of the active research questions, and the James Webb Space Telescope is definitely going to be probing this question. So we want to know when were the first black holes formed, and astronomers have found black holes when the universe was quite young. So say 100 million years old, which is very young compared to its present age, which is about 14 billion years old. So a couple 100 million is very small compared to 14 billion. But what we don't know is whether those very first black holes are sort of the cinders that were left over from the first generation of stars, which is probably how early black holes were formed. But it's also possible that black holes actually formed in right away in the early universe. I told you before, in the Big Bang, the universe started as this really hot, dense plasma, and then it expanded and spread out over time. Black holes could have formed in that process, and they're called primordial black holes. But we don't really know if that happened. Maybe it did. It's unclear.
And do they ever just kind of die? I don't know if that's the right term, but just cease to exist.
Cease to exist. So probably not, but maybe. So there's this idea that black holes could evaporate over time, but we don't have evidence that actually is the case. And that would only be the case for really little black holes. So the big black holes, even if they do evaporate, it would take so long that it's not anything we need to worry about, because it would take, much longer than the age of the universe.
Oh, and is it selective about what goes into them? What can fall into them?
Nope. Black holes will eat
They're undiscriminating.
anything. They're like the goats of the astrophysical world. They will eat anything. Totally don't care.
Okay, that sounds a bit scary to me, though. Like, are they going to consume a galaxy?
No, you don't have to worry about it. So if our sun tomorrow turned into a black hole, so that would be bad. It would be dark and cold. So fortunately, that's not going to happen. But the orbit of the Earth actually wouldn't change at all, because we're far enough away from the sun that even if it turned into a black hole, it wouldn't affect the orbit of the Earth. So you actually have to be quite close to a black hole in order for it to be able to pull matter into it or shred things or that kind of thing. It can affect the area around it, though, because when a black hole is growing, if you have that disk of gas and dust that's swirling around and glowing and giving off a huge amount of light, that can be very energetic. There can be X-rays and lots of radiation, that sort of thing. So it would be. I mean, we're very fortunate we don't live close to a black hole.
Close to a black hole.
Yes, but we don't have to worry about getting sucked into one. That's just, that's not going to happen.
And you're very interested in quasars.
Yes.
Why quasars? Like, what's so special about them that you're drawn to them?
I mean, when I talk to my students, what is not to love about a billion solar mass black hole? Like, how they're just
go for big or go home.
Yeah, exactly. So I would say for me, I'm really excited and drawn to the extremes, to things that are just not like, they have nothing to do with our daily lives. What happens near a black hole is nothing that any of us are going to experience in our life. And for me, that's just really intriguing. I'm just so curious, how do you actually grow a black hole? How do they wind up in the centers of galaxies? What do they come from? And one thing I study is the winds from supermassive black holes. So they actually drive these really, really fast winds, tens of thousands of kilometers per second. And then they go crashing into their galaxies. And so it's dramatic, it's exciting, it's extreme. And I'm really drawn to that because of that. I just think it's so interesting.
And how do you do most of your work?
So I am primarily an observer. So that means I use telescopes. I use all sorts of telescopes. I will use, I'm agnostic about telescopes. So I've used space telescopes and ground-based telescopes. Canada has access to the Gemini Observatory, which has two beautiful telescopes, one in Chile and one in Mauna Kea in Hawaii. And so I've used those telescopes and the Hubble Space Telescope. And in the near future, I hope to use the James Webb Space Telescope. So those are an X-ray telescopes. So all sorts of different telescopes.
Have you had moments in your work, in your research, when you came across something incredible that it just filled you with so much excitement?
Yes, it's for sure. So you get that but often it's a little, I would say sometimes it's delayed because it can take you a while to get from, okay, here's my data. I just got it off the telescope. Usually you have to do quite a lot of work before you can actually figure out what's going on. And then when you find something that's really exciting, your first thought, because you need to be a skeptical scientist, is, oh man, I messed something up. So,
okay, can I just stop you there?
Sure.
Is it because it is something that is not typical you're seeing? So you think it might be a mistake because the data shows you something unusual.
Exactly. And I would say that's the instinct of a good scientist. So, ooh, this is cool, but I better check because I probably messed something up. And honestly, like most of the time you mess something up. Like just honestly, like finding something extraordinary is something that maybe happens once in a lifetime, right? And finding that you made a mistake in your process happens very often. But I've had those moments where I figured something out, and it happens. If you're a student, for example, you go and you bring your discovery to your supervisor or your fellow students, and you say, "What do you think about this?" And then you have to make your case, right? You have to make your argument, and they'll push back. Did you do this? Did you do this? What about this? Have you checked everything? And so that's part of the process that is, in a healthy scientific community, you have that pushback, that sort of that optimism for the big discovery, but also the skepticism to make sure that, you don't want to have to retract your result in 6 months because you found a bug in your code, right?
See, I'm so glad that you explained that to us because I think, and for me too, initially, I thought a discovery was all about, oh, you're going to see something. It's going to be so obvious, like indisputable, as if, oh, I just discovered a planet. There it is. Like, you don't need any more proof than that. But it's not that way, is it? Most of the time, it's data you're looking at.
Yep, it's data. And you have to, and data can come from different things. It can come from a mistake. It can come from, some artifact in the instrument, some problem in the processing. And so those eureka moments look fantastic in movies, but in reality, they're not that distinct.
Yeah.
And
do you remember when they discovered the Higgs boson particle?
Mm-hmm.
Do you remember that? Yeah. So I remember that too. And when they first announced it, and I was in the media and it was being reported, and I thought, my automatic thought was, because I didn't know a lot about it, oh, they've seen it. Like they actually saw, but no, they didn't see anything. It was information they got. And then I was really lucky because I had a chance to go to CERN. And you've probably been many times.
I haven't been, but yes.
Oh, you haven't been? Oh my goodness. It was incredible. It was incredible. And I didn't even know the public could go, but the public can go and you can sign up for a tour, which is given by an actual physicist who takes you around there. And, you don't actually obviously go down to the Hadron Collider, but where, all this discovery was made. But they were talking about the Higgs boson and how they had all this data they had to go through. And then again, I guess they noticed something unusual. Which was how that was how the particle was detected because of this data that was unusual. And, it struck me too that I guess it was before the discovery, it was like 50 years earlier that someone had even come up with the whole concept of the Higgs boson particle. It had taken 50 years and I don't know, I'm sure millions, if not billions of dollars and scientists around the world and, the Large Hadron Collider. And I thought about that and I think about, with you too and all the scientists, you devote your life's work, your passion to this. And then maybe or maybe not, you're going to have that discovery happen, right? Maybe not even. What goes into that thinking, right? That kind of dedication and passion is something that may not even come to be.
Yeah, so I think that's an excellent point, and I would say that doesn't motivate me primarily. So I'm not motivated by having the big discovery and getting something named after me. So I'm motivated by uh, I'm just curious. So I just want to know. I just want to understand, and I have to say I feel so privileged that I'm able to do this as a job because I've just had phenomenal experiences. I love going to the telescope. So, we don't actually do it as much anymore as we used to because of the way things are set up now. But, going to the top of the mountain and waiting until it gets dark and, operating the telescope, and you can hear the rumble of the dome as it turns around so that the shutter is open and the telescope can look through it. That's just an amazing experience to be up there in the dark, looking out, trying to learn something about the universe. And the community that I'm a part of is also something I really love. That there are other people who are also curious, and you can, sit down and just hash out all of these obscure details about what quasars are like, and it will inspire passionate discussions, and so that there's something about being a scientist that's much more than just the discovery. It's being a part of the community. It's being curious and always challenged, and also working with students, which is another thing I love too.
Mm-hmm.
And I feel that in many ways, having your students go out and be successful and be find rewarding work. I mean, that's a big part of being in a university for sure, is having that engagement with students as well, and sharing the training and sharing the knowledge, and helping them develop so that they can be scientists on their own.
Study in space, it can take a long time. It can take a lot of money. Perhaps no guarantee that you're actually going to find out what you set out, to find. What is the argument that it is important, that it is critical to do this kind of work, even though it does take a lot of time and a lot of money?
So that is a great question. And I think there's lots of ways of answering that. So why do we do this? Why is it worth the investment of a society? We're asking the public to invest so that we can pursue discovery science. And I think there's a lot of reasons for that. So and some of them will resonate more with some people than others. So one is just it's valuable. We're human, we're curious. We want to understand how the world works. And this is part of the benefits of being able to do this, is that we are increasing knowledge, we are increasing our understanding of the universe, and this is something that we should recognize as being valuable. So the second thing is that science is an amazing driver. So when we're talking about space telescopes, for example, and we have a bunch of astronomers, and they are so motivated by trying to understand the universe. And so you have this amazing talent, and that will be mobilized in order to pursue that goal. And we don't get that many space telescopes. So when we put one in space, it needs to be a lot better than the telescopes that came before, because otherwise it's not worth it. It's expensive, it's hard, and these are special investments. So it has to be a lot better. And there aren't that many other places where you require something to be 1,000 times better, 1,000,000 times better before you're going to put it in space.
Yeah, that's a really good point too, because in pushing the technology, we are also, all of us, directly benefiting from the results of that. That's why we have cell phones. That's why we have other technologies, right, that help us. It's because of all the technology that was put into the space research in the first place.
Exactly. And that's and you can't predict. I think that's another thing. It would be great if we could figure out, okay, we'll invest in this technology for science, and we know that we'll get this downstream benefit. And that would be great, but it's not how it works, right? So you don't know which technologies are going to pay off, but historically they have. And usually it's only maybe one or two that pay off, but they pay off in a big, big way. So, lasers were developed originally for science. The whole technology of interferometry, which puts together the signal from two radio telescopes, it was originally for science. That's the basis for how an MRI translates a signal into images. So, I mean, if you had asked the radio astronomers, hey, what do you think people are going to use this technology for? This analysis tool that you've come up with, they would not have guessed medical imaging, right? So that's those sorts of things happen. There's lots of these stories, and they've been well documented, but you can't pick.
In your work, what is the question that you would like to see answered?
Oh, let's see. Only one?
One to start with. The next one.
So I would like to understand. How growing black holes really how they impact the galaxies that they live in. So that's something that is a driver for me. So I study these black holes and I watch them grow and I see how their winds, we can see the winds, we know they're really fast, but we don't quite know what they do. And so I want to understand just that, and also just the mechanism for how those winds are driven away from the black hole, and then what happens when they reach into the galaxy. What's that impact? So that's something that drives me. It may sound a little obscure, but it's something that's very motivating to me.
Yeah, and do you think, is it feasible that there is, you'll find an answer in the near future?
In the near future, maybe. I don't know. I feel we're making steady progress, so I'm just not sure what's going to be the point where we've sort of really figured it out. And that's I'm not sure, but there's been steady progress made, and we just keep getting these new fantastic tools that allow us to make more and more steady progress.
And I'm just thinking back to when I was asking you about, what was the biggest discovery in the last half century? With every big discovery that we make, does it then kind of change the way the science might be done, and the way perhaps the emphasis might change now because of this major discovery? Do you know what I mean? That the trajectory then kind of changes because now something's been proven.
Absolutely. And also, there's fashions in science, just as there are in anything else. So there are some areas of astronomy where there's still open, unresolved questions, but they're not as fashionable as they used to be because people have gotten excited about other fields. One of the great examples is exoplanets. So when I was a graduate student was when the first planets around other stars like our sun were first discovered. And that entire research area has just taken off. And now there are entire telescopes in space that are dedicated to finding more planets. And so that there's just a lot of people that are working in that field. And there are other fields where, there's still open questions and there's still things that need to be figured out, but they just don't have as much energy behind them because, the science has sort of moved on and there's other areas that are more exciting. But it doesn't mean they've solved all the problems. It's partially, it's just, what's fashionable, what's hot. We're just as susceptible to those trends as any other community.
What do you think? What do you think is the next big question that, if it were to be solved, would be a game changer?
Then what is dark matter? So this is one where there are lots of experiments. And these experiments are weird. So they've got crazy detectors in the bottoms of mines, buried under kilometers of rock. And so there's lots of ways where people are trying to do a direct detection of dark matter. And I mean, when that happens, that will be a big deal.
Okay, so for people who don't know, can you explain what dark matter is?
Sure. So when we watch the motions of, say, our galaxy, so our galaxy, as I said, it's a fried. It's shaped kind of like a fried egg, but then the whole thing is rotating. And if we look at the speed of the stars in the outer part of the galaxy, then what we see is those stars are going faster than we would expect based on all the light from all the material that we can see. And so that's evidence that there's actually more stuff in the galaxy that we can't see, but it's gravitational. It has mass. It's able to affect the motions of the stars in the galaxy. And so we call it dark matter. It's not really a very original name, but it's dark because we can't see it. And it doesn't emit in any kind of light. And people have looked, and it apparently doesn't really interact with normal matter, except that it has gravity. It has mass, so it pulls things in the same way that normal matter does. And we have no idea what it is. I mean, it's crazy.
Wow.
It's 75% of the mass in the universe. We do not know what it is. And so, but there are lots of experiments that are trying to detect it. And so if a dark matter particle were detected, that would be, I mean, a Nobel Prize for sure, but that would be really a game changer.
Do you dream about any of this at night?
Do I dream? Yes, but I dream about it in I think more of a fantastical way. So because the universe is so beautiful and it's so extreme, and just thinking about flying through a star forming region and flying around a black hole and what that must look like. Those are the sorts of
So
things.
it's not like you're dreaming about numbers. Thank goodness.
No, sometimes you do find yourself, trying to solve problems while cooking dinner or walking the dog, that kind of thing. But yes, my dreams, I think, are more visual and more fantastic than that.
Well, are you a fan of science fiction?
Oh, absolutely.
Ah, okay, you do. Well, so I don't know if you're a fan of Star Trek.
I'm a fan
Yes?
of different epics of Star Trek. But
Okay, because I think I'm pretty sure it was Star Trek that coined the phrase "the final frontier."
Yes,
right?
yes.
Yeah.
Mm-hmm.
Okay. So I mean, at this point, we're not living on Mars or any other planet yet. What do you foresee in the future? Do you foresee that kind of thing happening?
So I don't know. It's kind of tough. I would say one benefit of being a part of the Canadian Space Agency is I've been able to understand a lot better about what it's like to be an astronaut. I've met our Canadian astronauts who are all fantastic and impressive, and just learn more about what it's like. And it's really hard to be in space. So it's hard on your body. It's hard to be confined. It's hard to be in that environment that's kind of fragile, right? Where bad things can happen. And and then I think about being, on the moon or on Mars. And that is not, it would be extraordinary to experience that. But honestly, I would not want to live there. It would be
not in the near future, it sounds like.
No, I mean, we're so lucky to be on this planet, which, is lush and green and fertile, and we can breathe the air, and we can move around, and we're not, worried about being fried by radiation, or, any of the things that can happen in, so those environments are really, really harsh. And you would have to worry about the radiation. You'd have to be confined, and also the landscape is, Mars is beautiful in its own way, but it doesn't have any trees. And so
let's take care of our own planet then.
Exactly. But I think the possibilities for exploring the solar system, whether even if people don't go there, but exploring it robotically, is really exciting. Thinking about sending missions to some of the icy moons around Saturn.
And you mean
Jupiter.
with rovers and things like that? Yeah.
Exactly. There's going to be a helicopter that's being sent to Titan. So there's the moon of Saturn, one of the moons of Saturn. So there's lots of exciting exploration possibilities, even if we don't go there. And I think as an astronomer, maybe I'm I'm more at peace with that notion that I don't have to go there because the things I study, it's not even possible. So they're so far away. There's no way, I could ever visit. So I'm
Right.
content
Yeah.
with being able to study them from afar. And the same thing with the outer solar system. But I am sure that, humanity is going to be interested in exploring and sending people out into the solar system. I'm sure that will happen. And
I
it'll be
think
interesting
so.
to see what it looks like.
Yeah, I think so too. Yeah. Well, thank goodness in the meantime for telescopes.
Exactly. It allows us to look from the comfort of our own homes.
I so enjoyed this conversation. Sarah, thank you so much for sharing all your knowledge and your experiences with us.
It's my pleasure. It was lovely to speak with you, Mary.
That is Sarah Gallagher. She is an astrophysicist, a professor of physics and astronomy with Western University. She's also science advisor to the Canadian Space Agency. For more on Sarah and her work, you can check out our show notes. That is it for this edition of the Cram Podcast. Hope you enjoyed it. Our thanks to the Temerty Foundation for their generous support of the podcast. And you might also be interested in our literary podcast. It's called Passage to Wonderland. I highlight compelling passages from books that offer discovery, insight, and a sense of completion for the end of your day. You'll find Passage to Wonderland wherever you get your Cram podcast. Thanks very much for joining us. Hope to see you next time.